Good morning, folks.
Not bad. Good morning.
Fall has arrived.
Thanksgiving is around the corner.
Huh?
Thanksgiving is around the corner.
Thanksgiving is around the corner.
Yeah, Jack Frost came with the kneecaps this weekend.
Turkeys are hiding everywhere.
Yeah, they came out.
Huh?
We don't eat turkey.
You don't?
Fun fact.
We
all-
eat stuffed chicken breast.
Well, that's good too.
It's so good because I don't eat turkey.
My daughters have fish.
Kimchi. Fun fact. You know all the food we eat? When we break it all down, it makes us all tired.
It's because it takes energy. All right, folks, let's go ahead and get started. So, today, before we finish chapter 12, I wanted to go through a quick in-class example. So, I want you all to take 3 or 4 minutes and figure out what's in the boxes and figure what would be at the end of each arrow. Each of the end arrows. So this, we'll put a box here too. We'll make it simple. Figure out what goes in the boxes.
What chapter was ether in?
Ether is just diethyl ether, it's a solid.
Oh, okay. Huh? Well, it could be worse. We could be in here at 80. Which I highly recommend no freshman do, because that sort of strong will tell people unless you feel like
Look on your, focus.
I'm focusing. I like to talk while I'm working. Is that a hydrogen and oxygen?
What?
Is that a HOIC?
Here?
Yes.
That's water and a little bit of acid.
Is it a HO at the bottom?
No, it's H plus.
I would say that.
Another couple minutes.
Would we treat that as a vision problem?
It's a what?
A division problem?
Division?
Move over. Those two have two BRs.
All right, folks, let's go through this. We're going to start with this molecule. What's this molecule?
Cyclohexene.
Nope. Benzene, right? So it looks like a cyclohexane, but it's got 3 double bonds in the middle. It's got 4 units of unsaturation total. This is benzene. What's special about it?
Aromatic.
Yeah, it's aromatic. Right, so we're going to start off, we're going back in a couple of chapters, right? We're going to take benzene, we're going to react it with bromine in the presence of iron tribromide. What's the product going to be?
The ortho-dibromobenzene.
Why dibromo?
Dibromobenzene.
Yeah, it's just bromobenzene, right? Is the organic product. Yep.
Does it matter where we put it?
Doesn't matter where you put it, because no matter where you put it, it's the same thing. If you'd put it here or here or here, all I got to do is just turn it and you get the same thing, right? So you got bromobenzene. Now, of course, to take care of everything, iron tribromide, of course, is catalytic. What happens to the other bromine? It becomes HBr. So there's plus HBr. But we're going to assume that we work it up, we get rid of the HBr. We're only interested in the organic piece, which is this. Right up here, right? That's all we're interested in. So, that's not a double bond or anything, that's just trying to show you. Okay? So that's what we're interested in. What happens in the next step?
Mg gets added.
And I make what? Where does it get added?
Inserted between the bromo and the carbon.
Yeah, and so we make that, right? What is that called in general?
Organometallic.
It is an organometallic species because I've got a carbon metal bond, right? But in general, what are these reagents named?
Grignard.
Grignard. Yeah, after Victor Grignard, who discovered them. And how do they behave? How do they like to react?
As if.
How do they like to react?
Carbonyl.
Okay, they behave like carbanions.
Carbanion.
That's true.
That's it.
That's true. So it's almost like that carbon that has the metal is carbon negatively charged, right? Okay.
We make a carbon-carbon bond?
They can make carbon-carbon bonds. That's true. What else?
We make alcohols?
Yeah, we'll get to that in the second step.
Nucleophile.
Yeah, they're nucleophiles, right? These behave like nucleophiles. So I've got a nucleophile here, right? And we can think of that as minus plus MgBr plus. You can think of it like that. It's not really that, but that's how it behaves, okay? So we just made a Grignard reagent. If I take this Grignard reagent and I react it with this aldehyde called formaldehyde, what's the product? Uh-huh.
Benzyl.
What kind of alcohol?
Oh, never mind.
First degree alcohol.
Okay, yeah, primary. So I'm going to end up with where this carbon is this carbon right here. So you can see the 2 hydrogens that are attached to it. The oxygen is still there, right? So the nucleophile attacks, breaks the weak pi bond, and then it's the second step that puts the hydrogen on the oxygen. All right, notice that at step 1 and step 2, it's not all together. So,
Bless you.
the take-home message here is that a Grignard plus formaldehyde gives a primary alcohol. All right. Now, if I take this nucleophile, this Grignard reagent, now I react it with a regular aldehyde. Okay, this is acetaldehyde. What's the product?
Secondary.
A secondary alcohol, right? So if I draw that out, carbon is this carbon, right? You can see that the CH3 is still attached to that carbon just like it is here. There's a hydrogen here that I haven't drawn in, it's still there, and the oxygen is still there. So I made a secondary alcohol.
And the 1% alcohol has 2 H's,
The top one? Yeah. 2 hydrogens, yep.
2 hydrogens. And the bottom one has 1.
Yes, that's correct. Now if I add the nucleophile to a ketone, here I'm using acetone, what's the product? It's a tertiary alcohol, that's right. So we're going to have where this carbon is this carbon. You can see the 2 methyl groups are still attached, the oxygen is still attached, and we get a tertiary alcohol. Okay? It's chemistry like this that ketones and aldehydes like to do. They like to do addition, they like things to add to them. Okay?
There's 4 hydrogens in that one, right?
Pardon?
How many hydrogens? 2?
On this one?
Yes.
No, none.
None.
These
So
are 2
one-
methyl.
So
2 hydrogens,
2,
1 hydrogen, 0 hydrogens. Yep.
negative.
Yep. Primary, secondary, tertiary. Notice how things are connecting together. We learned how we could do this kind of chemistry. What was this chemistry called in general? This first step.
Catalyst.
Well, this was a catalyst, yes, but it was.
Electrophilic.
It's not addition because we're not adding anything. We're substituting, right? So it's some type of substitution.
Electrophilic.
Yeah, this is electrophilic aromatic substitution. Right? We talked about that in a previous chapter. Made a bromobenzene, then we made a Grignard out of it, and then we added that to different types of carbonyls. And we got all kinds of different products. Okay? Does that make sense? People want to take pictures because I'm about to erase.
Let me write down that real quick, sir. I appreciate you saying I'm away man so people can take pictures. I appreciate that. I don't have any pictures today. The picture is not gonna last. It's not gonna be on.
Sure.
Got it? Got it, Dakota?
Got you too.
Ow.
It's not the only kind of chemistry, however, that carbonyl compounds can undergo. They can also undergo these types of reactions that we're going to talk about today. We're going to talk about the formation of so-called hydrates and acetals. We're going to talk a little bit about the formation of amines. I'll give you a biological example of why that's important. And then we'll talk about using so-called hydrides to reduce carbonyls. Okay, so we'll talk about all of these today, wrap this up, and have our quiz from last chapter and get our way. Now it turns out that you can take a carbonyl, be it a aldehyde or a ketone, and you can actually add water across the carbon-oxygen double bond to make what's called a gemdiol. J or G-E-M stands for geminal, okay? Meaning like Gemini is twins, okay? So, is there anything really unique about this? You've already learned this, you just don't realize it. Where did we add water across something before?
Hydration.
Hydration of an
Alkene.
alkene, right? It's just a carbon-oxygen double bond instead of a carbon-carbon double bond. We're just adding water across the carbon-oxygen double bond. This is called hydration, just like it was when we did the addition of water across a carbon-carbon double bond, okay? You typically have to have a little acid for this to work. You don't need a whole lot, it's catalytic. And so sometimes when you put a ketone or an aldehyde in water, it will form these so-called hydrates pretty easily, okay? However, it's very important to note that most ketones, where R prime and R are both carbon, the equilibrium does not favor the formation of the hydrate, okay? The equilibrium constant is much less than 1. Most of these things exist as the ketone. So, when you take your acetone-containing fingernail polish remover and you put it in water, it stays as the ketone. Okay, it doesn't form the hydrate to any appreciable amount. But some things do form these hydrates very, very easily. And so, let's take a look at some of those. So, for example, if I take formaldehyde and I place it in water, what you find is that it has a very large equilibrium constant, okay, or apparent equilibrium constant, which means that the hydrate is in much greater concentration than the ketone. So when you all go to your biology lab and you're dissecting a frog and they say it's in formaldehyde solution, it actually isn't the aldehyde to a very great extent. It's mostly the hydrate. Acetaldehyde, it favors the formation of the hydrate as well. Okay, but notice that's a big difference. You know, 2 times 10 to the third, that's 2,000. 2,000 versus 1.3, that's a huge difference, right? So even though there's a little bit of an excess of this over this in acetaldehyde, it's not to the same extent as you would see for formaldehyde. So what's the difference? This CH3 group, right? And it's bulky, right? So it kind of gets in the way, helps hinder this. If I take the fingernail polish remover, right, the acetone, you'll notice that it is 0.002. It's really tiny. 0.002. So very tiny, very little of it forms the hydrate. All of it stays as the ketone. Okay? Now if I go just to an aldehyde, just like we had here, right? Except now I add some more carbon. Notice that the value goes down. Why did the value go down by just simply adding a carbon? It got bigger and bulkier, right? So the value goes down a little bit. If I add a real big group, like a tert-butyl group, right? It's big, it's got all these carbons hanging off of it. You'll see that it goes down even further. And if I add something like this, these electron withdrawing groups, these chlorines, you'll notice that it goes way back up. That's almost, 30,000 as value. So electron withdrawing groups favor this. So the take-home message here is aldehydes like to favor the hydrates, and things that have electron withdrawing groups on the adjacent carbons will also favor the hydrates. So let's look at some real simple examples. So here we have, again, formaldehyde, right? You place it in water, 99.9% of it is the hydrate. If you place acetaldehyde in water, about 60% of it, just shy of 60%, is going to be the hydrate. So you go to the bar, you drink your favorite shot, your liver oxidizes the ethanol to acetaldehyde. The acetaldehyde ends up in the bloodstream. 60% of it will be hydrated. That's why you get a hangover. It's called dehydration.
And also your liver becomes a rock.
Well, we're not going to talk about the biology of all this, but that's what happens. Is you get dehydrated. Your blood volume decreases a little bit, right, and you start to have headaches and all kinds of stuff.
That's why you eat before you drink.
Eat or yeah. And then, of course, here we have a ketone, acetone. Only 0.2% of it is going to be the product. Okay, so very little of it actually forms the hydrate. So let's work our way through the mechanism. And let's take acetaldehyde. Let's do that one. So I've got water, I've got a little bit of acid. I'll just put a little squiggly line there to show you all we need is just a little bit. Most water is acidic enough for this to happen. Okay? How do I add water across the carbon oxygen double bond? What's going to happen first?
Well, since you have water, there's gonna be another H up there. That's H is gonna be added to that O, so it's gonna be HO. It's gonna be X. Or
Well, that's ultimately what we're going to get. Let's walk our way through the mechanism.
Well, water is not a very good nucleophile.
It's not a very good nucleophile, is it? Why isn't it? Why isn't it not a very good? Why is it not a very good nucleophile?
It doesn't have a negative charge.
It doesn't have a negative charge, right? And what else?
Isn't water a good leaving group?
Water's a good leaving group, yes. Yeah, we talked about that.
Yeah.
Yeah, water itself is a good leaving group. What else? Oxygen's electronegative, right? It wants to hold on to those electrons.
Yeah.
Yeah, so it's overall not a particularly great nucleophile. So how do we do this?
Possibly.
The double bond for the oxygen,
Pardon?
break the double bond.
All right, we need to weaken that double bond. I'm not going to say we're going to break it yet, but you're on the right track. How can I weaken that carbon-oxygen double bond?
The electrons from the oxygen try to the H plus.
Yeah. So we can put a proton up here, right? So in the first step, I do this. Right, and this is actually reversible. It can go back and forth. I need to draw my hydrogen in better. There we go. Hydrogen. How does that weaken the carbon-oxygen double bond? The pi bond. Why does that weaken it? What do you know about oxygen on the periodic table? Where's it at?
Electronegative.
It's over here. It's pretty electronegative, right? So we just put a positive charge on an electronegative atom. Is that going to be good or bad?
It's not happy.
Stable.
It's not happy, right? So if it's positively charged, what's it going to do?
Pull
Pull electrons towards itself, right? Where can it get them?
from the pi bond because it's the weakest.
That's right. So it's going to pull electrons from the pi bond. And you can actually draw this out where you have a resonance structure. Where you put a positive charge on the carbon.
I think you missed the carbon right there. It's only it's 3. It's 3C.
Yeah?
Oh. Wait, isn't there another carbon?
Oh, yeah. Yeah, you're right. Okay, so we can think of this. So now what happens?
The nitrogen.
The oxygen from the water can attack the.
Yeah, this is a weaker bond now, right? It's got we can draw a resonance structure where the carbon has a positive charge on it, right? So we can have the nucleophile attack the carbon, break that even weaker pi bond, okay, and we get if we've got H plus, of course, we've got to have a little A minus somewhere around there, right? We've got to have a counter ion. So now what happens? We're almost there, right? We're really close to there. We've added, it kind of looks like, what do we got to get rid of?
The hydrogen.
We got to get rid of one of these hydrogens, right? I told you it was catalytic in protons, so I got to get it back, right? So I've got to have something come and take it away. And so we can have the counter ion just come in, and we end up with OH plus our HA, which is our catalyst to start with, right? So we're good. Do you have a question?
Can we go over the last part again?
This part?
Yeah, from there.
I gotta get rid of that hydrogen, right, or it's not a hydrate, it's protonated.
So we added from after the resin structure, we added the water to the molecule,
Mm-hmm.
and then,
That's how we got this bond right here.
okay. And then the hydrogen is moving because of the anion.
Mm-hmm. And you end up with the hydrate. Yep. So this is perfectly reversible. We could go in the exact opposite direction and get water back if we needed to.
How did we get the second elevation?
Here,
Yeah.
by losing the proton. See?
Oh, that's the OH bond,
Yeah.
it just doesn't draw like the bond.
I can draw them like that too. That's not a plus. Does that make more sense?
It makes sense both ways, it's just because we drew it like that here.
Mm-hmm. Okay. All we're doing is adding water across the carbon-oxygen double bond. Okay? Where the oxygen ends up getting the hydrogen, and the OH goes to the carbon.
What's the HA over there?
It's the acid catalyst. So it can be anything. A can be anything. You can use a little HCl, you can use a little HBr. It really doesn't take much for this reaction to occur. It's just catalytic in it.
Why is the arrow to that H?
Here,
Yeah, well,
I was just showing you that we get back our HA,
oh,
so this is catalytic. That's not a reaction arrow, I'm just pointing to it. Okay. So that's the mechanism of adding water across a carbon-oxygen double bond. Now, if I can add water across a carbon-oxygen bond, what else must I be able to add, you think? What else looks like water but isn't water? What other functional group?
Ether,
Does ether look like water?
somewhat.
Somewhat. It's got oxygen, but everything that's got oxygen doesn't look like water, right? What's special about water?
Hydrogen bonds.
It's the oxygen bound to a hydrogen, right? Or two hydrogens. What else has an oxygen bound to a hydrogen functional group that we've talked about?
Alcohol.
Alcohols. So if I can do this with water, I should be able to do this with alcohols. Okay? And in fact, we can. This is called the formation of acetals. Okay? And in general, you'll hear me use the word acetal, but technically there are acetals and ketals. Can you tell me the difference? That's right. So an acetal is formed by the addition of alcohol to an aldehyde, and a ketal is ketones. Yeah, so we can do this with both ketones and with aldehydes, but for whatever reason, chemists typically just call all of these things acetals.
Is that HA?
Mhm. It is. And so I can take an aldehyde or a ketone, and I can react it with two molar equivalents of some type of alcohol in the presence of an acid catalyst, and I can make what's called an acetal. Okay? And this is, again, is perfectly reversible. But what do you notice about this reaction that's different from the hydrate formation? What's the other product that I have?
Water.
Water. Notice there was no water as a product in the formation of a hydrate because you're adding water across a carbon-oxygen double bond. Okay? So that OH that was or that oxygen that was originally in our starting molecule stays. Okay? This oxygen right here is the same oxygen that was the ketone's original oxygen. It loses it overall. Okay? You might ask, how do we know that? We know that because we've made ketones that have what's called oxygen 18 labeled. Okay, and so oxygen is 18 is an isotope of oxygen that we can detect, and we know that that oxygen ends up 100% in the water. Okay, these reactions are also called condensation reactions. Can anybody tell me where the name condensation comes from? What do you think of when you hear the
Water
word?
leaves.
Yeah, water leaves. You think of condensation like if you're in the shower, right? Condensation forms on your mirror or whatever and it runs down, right? The same thing happens here when you run these reactions. When you run the reactions, you'll notice water forming and it looks like it's condensing like it would on a mirror, okay, from the vapor. So you'll get this liquid water in your product that you have to take care of. Okay? These are not ethers. Carbon, oxygen, carbon, you might think that's an ether and that's an ether. But since one carbon has 2 bonds to oxygen, it has a common, right? These are not ethers. These are called acetals. They are a different functional group. Okay? They are a different functional group.
Why again? Can you explain that? Is it because there are 2 more R groups?
Not because there are 2 more R groups, but because this carbon shares 2 bonds to oxygen, single bonds to oxygen. This is the acetal functional group. Okay? It's not 2 ethers connected together. This isn't one ether and this another ether just sharing 1 carbon. This is 1 acetal. Okay? So the chemistry of acetals is quite different than the chemistry of ethers. Okay? They don't do the same thing. Okay? And so, for example, you can take this aldehyde. Okay? We can take methanol. Usually what we do is we just use methanol as the solvent. Okay? It says 2 equivalents here. That's the amount you have to have. But a lot of times we use excess. And then we use this acid called tosic acid, TSOH. All you need to know is that that is basically organic sulfuric acid. Okay? Tosic acid looks like this. Okay? It's a strong acid, just like sulfuric acid is a strong acid. Okay? But it is the acid, for whatever reason, that organic chemists like to turn to. I say for whatever reason. I can tell you for what the reason is. Has anybody ever worked with sulfuric acid? Yeah, if it gets on you, it will eat through your clothes, it will burn, causes serious burns. It's a liquid. You have to pour it. You pour things, you tend to splatter. Tosic acid is a solid. Solid, I can take a spoon, I can dip it out easily without having to worry about getting it on me. I can weigh it out easily. I don't have to worry about splashes and splashes and all that kind of stuff. So it's just a more convenient form of sulfuric acid, if you will. Okay?
Would it do something to your skin if you touched it?
Oh, sure. Yeah. I mean, it would burn you if you got it on your skin. But pouring the liquid, I mean, things splash and splatter. It's a lot easier for it to get on you than when a solid does. Yeah, you definitely don't want to heat it or anything. It's not healthy for you. Okay. We can also do these reactions where the 2 alcohol groups are part of the same molecule. Okay, so here's an example where we took cyclohexanone. Okay, so cyclohexane with a ketone, that's cyclohexanone. We take this molecule called ethylene glycol, which is just 2 alcohols connected together, tosic acid, and we get this acetal. It's just that we get what's called a cyclic acetal. Okay, it's part of, you make this 5-membered ring. Okay, it's still the oxygens are still geminal, just like in a hydrate, except there's no hydrogens on the oxygens, right? You've got this cyclic acetal. This is a common reaction that's done in organic chemistry to quote unquote protect a ketone. Okay? And we'll talk a little bit about that at the end of the day. Okay? If you had a ketone in your molecule that you didn't want to react, but it would if you didn't do something to it, you can protect it as an acetal. Okay? Because I can get my molecule back by just adding in a bunch of water, and I can drive the reaction in the reverse direction. Okay? So if I took my ketone, I added ethylene glycol, tosic acid, and I removed the water, all of this goes in this direction, and you form the cyclic acetal, 100%. It goes very, very well. When I want to get my ketone back, all I got to do is dump it into a huge amount of water, and the equilibrium will shift back. So it's a great way of protecting these groups from chemistry that you don't want to happen. And the reason is, right, we know that the ketone has a weak pi bond. this has no weak pi bonds anymore. It can't do any of the chemistry with Grignards or anything like that at this point. Okay? But what's the oxidation state of this carbon versus this carbon? Let's calculate the oxidation state of both of those molecules. So we want to know the oxidation state of that carbon. What do I do? How do I calculate the oxidation state?
Side.
We
Right.
got 4 minus 2
It's 4. Where did you get the 4?
for carbons, it's the valence.
Valence electrons, right? And so does it own any of these?
No,
No.
How many of these does it own?
1 and 1 because 2 more carbons, 1 minus 2, so 2.
That's right. So this molecule, that carbon is in the +2 oxidation state. Okay? Now let's look at the acetal. Okay, so we come in and we do it again. 4, right? Does it own any of these? Does it own any of these? Does it own any of these?
No.
Yes.
1 and
1 and 1.
it's the same.
They are both in the same oxidation state. That's why we can use it as a protecting group. Okay, I just took away the weak pi bond for a while. Then I go do whatever chemistry I want to it that this might have gotten in the way of, and then at the end I can convert that back to that because it's an equilibrium reaction. Okay. Anybody know what ethylene glycol is used for or has been used for? The car? Yeah. What about the car? It used to be used as antifreeze. That's right. We no longer use ethylene glycol as antifreeze. Can anybody tell me why?
Because it messes with battery.
No, it doesn't mess up with the battery. Turns out that ethylene glycol is quite toxic, and it's very sweet. I've actually tasted it before, a little bit.
Wait,
It's-
antifreeze?
Just a little bit. Don't ever do it. Okay? But ethylene glycol, is very, very sweet. It's about as sweet as sugar. And so people used to change their antifreeze in their car, and it would be in a big pot pan, and then dogs and cats would come and lick it and keep licking it and keep drinking it, and it would kill them. Little kids would find it in a bottle in the garage, and they would taste it, and it would be sweet, and they would keep drinking it.
Time period around 9:45,
Pardon?
9:50.
What?
Time period.
What about it?
That'll be around the same time regulations for all things call-wise will be settled.
I don't know. Now we use propylene glycol, which is less toxic and less sweet. And so it's much, much better for the environment, for the animals, and for little kids. Okay? So, but these are, the take-home message there is these are useful molecules, and they've been used in the past for a variety of reasons. We can also add primary amines to ketones and aldehydes to make new functional groups. Okay? Amines are nucleophiles as well.
So do we need to know the mechanism for these reactions?
I show you the mechanism, but I haven't given you any mechanistic questions on anything yet, so probably not. In terms of being able to reproduce. Now, you need to know the mechanism sometimes to figure out what's going on,
Yeah,
but I'm not going to ask you to give me the
Give
mechanism.
you, okay.
Okay? So, we got to refresh our memory on what a primary amine is. Remember, a primary amine is an amine that has one carbon-nitrogen bond. Okay? And an amine must have a lone pair of electrons, right? So this is a primary amine. It's 2 hydrogens, a nitrogen, lone pair of electrons, and one bond to some kind of carbon.
So it's the opposite for what we learned earlier.
This is exactly what we learned earlier for primary amines.
My bad.
Right? This is exactly that slide from when we talked about amines. Okay?
I retract my statement.
Okay. And of course, we can remember that secondary amines, right, have 2 carbon-nitrogen bonds, and tertiary amines have 3 carbon-nitrogen bonds. But what we're going to focus on today is just primary means. So be able to identify a primary mean, okay? If you take a primary amine and you react that with a ketone or an aldehyde, you're going to get what is known as an imine. I-M-I-N-E. It's a new functional group. Okay, we'll see the structure in just a moment. An imine. So you need to know that an aldehyde or a ketone plus a primary amine, I'm going to get an imine. That's going to be the result of the reaction. These imines are also called Schiff bases. That's just kind of slang talk. I am sure there's a chemist called Schiff. I've never done the research on it, and I'm sure he's the first to have discovered it. Okay? And it's so old, I am sure that it is a he, because this was a very male-dominated field 100 years ago. Okay? So, you can hear me call them Schiff bases, or you can hear me call them imines, but for the purposes of this class, on the exam, I will call them imines. Okay? So here's the example. We can take an aldehyde or a ketone. We can take a primary amine. You have to have a little mild acid. What do I mean by mild? Not very much of it. So a little bit of taustic acid, or TSOH, little sulfuric acid, not much, okay? In fact, when I used to do these reactions, I did these reactions when I was in graduate school. We made a lot of imines. I actually just rinsed my glassware with acid and then dried it. There was enough acid coated on the glass for this to work, which made it kind of convenient. Okay? But you'll notice that what is going to happen is you're going to replace the carbon-oxygen double bond with a carbon-nitrogen double bond. That's what happens in the formation of imines. And we lose water. So is this a condensation? Yes. This is a condensation. Okay, when I take alcohols and I react with aldehydes and ketones, I get an acetal plus water. Okay? When I take a primary amine, I get an imine plus water. Okay? These are also perfectly reversible. They're not drawn here as reversible, but if I dumped in a ton of water to an imine and let it sit for a while, it would all revert back to the ketone or the aldehyde. A perfectly reversible reaction. Okay? And so to go from here to here, all you got to do is remove the water, which is pretty easy to do. Okay? So here's the mechanism. Okay? It's nucleophilic. So you've got the carbon-oxygen double bond. You've got the lone pair of electrons on nitrogen. Nitrogen's a good nucleophile. The nucleophile attacks the carbon of the carbonyl, breaks the weak pi bond. You get this intermediate. Notice I've got an oxygen with a negative charge and a nitrogen with a positive charge and two hydrogens. Oxygen with a negative charge is like hydroxide. Is that a good base or a weak base? Weak?
Very good.
It's a very good base. I have positively charged nitrogen, right, with hydrogens on it. You think that's going to be an acid or base? Acid. Right? So I've got an acid and I've got a base. What do we know that acids and bases like to do with one another? They like to react and neutralize one another, right? That's called a proton transfer. The hydrogen from this acid goes to the base, and you end up with this intermediate called a carbanolamine. Okay? Carbanolamine. That's not very stable, and it reacts again. So the oxygen of the alcohol picks up a proton from the acid. Water, as Selena said earlier, is a good leaving group. Right? So I've got a good leaving group right here. My nitrogen actually is a good nucleophile, so it just attacks itself, kicks out the leaving group, kind of like an SN2 reaction. Okay? And I end up with the carbon-nitrogen double bond. It just happens to be positively charged here because of the remaining hydrogen. Water comes along, or the anion from the base comes along, plucks off this hydrogen, and you end up with the imine. Okay? It is catalytic in acid. Okay? You need a little acid, and you get a little acid in the end, and so you end up with these so-called imines. Okay? What you need to know is that wherever that carbon-oxygen double bond is, that's where your carbon-nitrogen double bond is going to be. There are no carbocation rearrangements. There are no funny business going on. It's very simple. Wherever you have the carbon-oxygen double bond, you are going to have the carbon-nitrogen double bond. Whoops, I meant to move that slide. Sorry about that. We'll come back to that later. This is very important for your eyesight. This is how you see. You have a protein called opsin that is responsible for the nerve sending a signal to the brain about your vision. Okay? I am certainly not an optometrist or an ophthalmologist, so I don't know all of the biology behind this, but this is what I do know. I know that opsin has a primary amine on it that ends up reacting with an aldehyde to make this imine. Okay, so this comes from, anybody know what? This comes from carrots, right? What is that? Beta carotene, right? So you eat beta carotene, your body processes it, it cleaves it in two, makes it into two aldehydes. You end up with a vitamin, I forget which vitamin it is. One of you probably know better than I do. And the opsin will react with that aldehyde to make this complex. Okay, so you've got opsin attached to this. This piece right here is what is responsible for your eyesight. So you'll notice that you have a cis double bond that's kind of crowded. This methyl group is getting really close to that hydrogen and it crowds it. Okay? It doesn't like that. But what can happen is that a light, H nu stands for a photon of light, a photon of light comes into the eye, hits this complex, and it actually flips the double bond from being cis to the more stable trans double bond.
Pretty neat.
Pretty neat. And so when that happens, the pi bond breaks, the molecule rotates, and then it reforms the double bond again. That's what the photon does. And when that changes, it changes the shape. And it kind of tugs on the protein a little bit. And when it does it, it fires a signal to the brain. That's how that works. The bad news is that if this was it, you would already be blind in life. You would have been blind about 3 seconds after birth. Okay? So what happens is, right, we've learned that forming imines is reversible. So what happens is once this forms, your body reverses this, cuts this piece off, and replaces the opsin with a new piece from your beta carotene that you ate 2 or 3 days ago or however long ago it was, right? And so that's how this all works. Your body depends on imine formation, or your eyesight, I should say, depends on imine formation, and it also depends on the fact that that's reversible. If it wasn't reversible, you'd see for a few seconds and then you'd be blind the rest of your life. Not much of an evolutionary advantage to that. Okay? So, having this type of functional group makes a lot of sense here because it's perfectly reversible. Any questions about that? All right. The other thing that aldehydes and ketones like to do is they like to be reduced. Okay? They like to be reduced. And one of the ways in which we can reduce them, okay, you might imagine, is that we could take a ketone. For example, let's just take cyclohexanone, and we could reduce that to an alcohol. What have we added across the carbon-oxygen double bond here? H2. So you might think, well, all I need is H2 gas and palladium or platinum, and I could do that reaction. And you would be right. The problem is that this reaction requires high pressures of hydrogen. It typically doesn't work very well with low pressure. Okay? So you typically have to put a lot of hydrogen gas in, pressurize it for this to work. And people typically don't like working with gases if they don't have to. Okay? But it turns out there's another set of reagents that we can use called hydride reagents. Okay? And there are 2 of them that I'm going to hold you responsible for. There's actually a whole catalog of these things, but there are 2 common ones. Sodium borohydride, NaBH4, and lithium aluminum hydride, LiAlH4. Okay? you will find me referring to lithium aluminum hydride as LAH. That's the common abbreviation for it. I will hold you to that on an exam. If I say this plus LAH, no, it's lithium aluminum hydride. Okay? These two reagents will reduce a carbon-oxygen double bond into a alcohol. So I can take an aldehyde and I can reduce it with sodium borohydride or lithium aluminum hydride, and I can get a primary alcohol. Or what did I say? Did I say formaldehyde or aldehyde?
I don't remember.
I don't remember. If I said an aldehyde, you would end up with a primary alcohol. Okay, and so that's how these work. You can think of these as, they're called hydrides because you can think of the hydrogen as having a negative charge on it. Okay, and it can function as a nucleophile. So let's work through the mechanism. Anytime you see LAH or sodium borohydride, think of H minus. What I'm about to tell you is a little bit of a lie, but it's a lie designed to help you understand what's going on. In solution, there is no H minus floating around. Okay? But this is how it behaves. So, what's going to happen in the first step?
The H is gonna attack something.
What's it going to attack?
The carbon.
Why the carbon and not the oxygen?
Because the carbon wants to like, the oxygen is more electronegative.
It is. So why didn't it want the electrons from the hydride?
Because it doesn't want to share.
It's gonna have too
Okay,
many.
that's good. Huh?
It's gonna have too many.
I could draw a mechanism. I could draw a perfectly reasonable mechanism where I get that. But why isn't that right?
Because carbon won't want to form a negative ion.
Okay? But if it goes the other way,
Ah.
right? So yeah, it attacks the carbon. And then in the last step, we add water, usually a little bit of acid, and the O minus picks up a proton from water. And so we've just added H2 across the carbon-oxygen double bond without using hydrogen gas. Okay. We just added H2 across the carbon-oxygen double bond without using hydrogen gas.
No, like, can you repeat the process?
From here,
Yeah.
so the hydride attacks the carbon. Hydride's a good nucleophile. Breaks the weak pi bond, you end up with the alkoxide, the O minus. Now we've got a new carbon-hydrogen bond here. And then this oxygen anion picks up a proton from our acidic water and gives us the alcohol.
You do it as benzene.
Oh, did I draw it as benzene? Thanks for catching that.
And so this happens when we use LAH?
Happens when you use any of these hydride reagents that we're talking about. Sodium borohydride or LAH, both of them work.
LAH or NADH4? Those are the two that do that?
And there are others, but these are the only two that I'm going to hold you responsible for. What I will tell you is that these both behave the same in terms of what they do, but the extent to which they, or the vigor with which they do it is different. So sodium borohydride, you can actually run that reaction in the presence of water. So you can take your aldehyde or your ketone, you can put it in water, and you can add sodium borohydride and this works. You cannot do that for LAH. LAH reacts with water so vigorously that it spontaneously combusts and bursts into flame, okay? So these are very different in terms of the reactivity. Okay, sodium borohydride is fairly mild. Lithium aluminum hydride is very aggressive. Okay, and sometimes you need an aggressive hydride reagent because for various reasons. But that's how these reactions work. Okay, sodium borohydride is also much cheaper than lithium aluminum hydride. And so you will, if you were to come up to my lab, you would find that we have a bucket of sodium borohydride actually, and a small can of lithium aluminum hydride because we use sodium borohydride quite a bit. But it will do this reaction, okay? So the take-home message here is I can take an aldehyde or a ketone and I can convert it into an alcohol, right? I can convert it into an alcohol pretty easy by hydride reduction. I hope you're getting the take-home message that ketones and aldehydes can give you a variety of alcohols. I can add Grignard reagents to make alcohols. I can add hydrides, react with hydrides and make alcohols, right? So they like to do that kind of chemistry quite a bit.
But are these hydrides LAH and BH?
They are hydrides.
They're hydrides?
They are hydrides, yeah. So we just went through the mechanism, but that's how you think of it. You think of that as H minus. Okay? How many H minuses do you think I can get out of sodium borohydride?
1. Out.
4.
Out.
How many do you think I can get out of lithium aluminum hydride?
1?
4.
I didn't see the, I didn't see the.
So if you had a mole of ketone that you wanted to reduce with sodium borohydride, you only need 1/4 of a mole of sodium borohydride. Because each mole of this can deliver 4 moles of H minus. Okay? So that's the mechanism. Here's where it becomes kind of important. Here's some real world examples. So industrially, they take this ketone. Notice it's a ketone with a benzene ring. Right? How is the ketone and the alkyl group situated? Are they orthomet or para to one another?
There.
Para.
They are para. And they actually make this by Friedel-Crafts acylation. Okay, so they take the benzene molecule that already has this on it, and they react it with the acid chloride and the aluminum trichloride, and they do the Friedel-Crafts chemistry, and they get this product.
I apologize. Is that in a Catashat thing?
This? Yes, it's a salt.
So is that line?
Na plus, and this is attached here, and then this is lithium aluminum hydride.
Oh, so that plus access thing.
It's positively charged.
So does it need a line?
No, it's not bound with a covalent bond, it's an ionic bond.
Okay.
So they make that industrially, very, very easily. And then they use sodium borohydride. Instead of doing this in water, they use methanol because this doesn't dissolve in water. But they use methanol. And they add the sodium borohydride and they reduce the carbon-oxygen double bond to an alcohol. And they get, what kind of alcohol is this?
Secondary.
It's a secondary. So ketones get reduced by hydrides to give secondary alcohols. Okay? Aldehydes would get reduced to give a primary alcohol. Okay?
Another question, out of 4?
Wait, is that
Yes.
any aldehyde? Because when we
Yeah.
were doing the other ones, it was only formaldehyde that gave you that.
Well, let's do that. It's a good question. So if I took benzaldehyde, this time I will draw benzene, and I put an aldehyde out here, right? And I react this with sodium borohydride and methanol, right? What's the product going to be?
Secondary. Wait, no. Primary.
I'm going to reduce this carbon-oxygen double bond by putting 2 hydrogens across it, right? Let me make this a big H, which comes from the sodium borohydride. What kind of alcohol is that?
Primary.
That's primary, yeah. It's only got one carbon bond.
We're using formaldehyde, right? Or benzo.
This was using this, yes.
So that holds true then, whenever you use formaldehyde or any form of formaldehyde, it gives you primary,
So if I used formaldehyde,
you get a primary alcohol.
I would get methanol, yeah. And that is just methanol.
But if you use any other aldehyde, you get a second degree? Or-
No, if you use any aldehyde like this, you will get a primary. If you use a ketone, you will get a secondary. Right? This was a ketone. You got a secondary alcohol. This is just methanol. It's not primary, secondary, or tertiary because there's no carbon-carbon bond. Right? Methanol is its own class. Any other questions? Whoop. Didn't finish this one. So then they take this, and then through several steps that we won't need to talk about, they actually make ibuprofen, which many of us take quite regularly, right? Helps in inflammation, headache, fever, all that good kind of stuff, right? But they make it in 3 steps from this molecule, which comes from the sodium borohydride reduction of a ketone, okay? That is how they do this industrially. You can buy sodium borohydride in bulk. It's pretty inexpensive, and you can do this kind of work pretty easily. You'll also notice, in this case, notice I've got a carbon-carbon double bond and a carbon-oxygen double bond. If I had tried to do the reduction of this ketone to an alcohol using hydrogen and palladium, what would happen?
Both
Carbon.
double bonds would be
Yeah, both double bonds would react, and I'd actually end up losing this carbon-carbon double bond, right? But they want it in this step. They want just the alcohol to be reduced. Sodium borohydride doesn't reduce carbon-carbon double bonds. It only reduces the carbon-oxygen or the carbon-nitrogen double bond, which we won't talk about. But I can reduce this selectively and get this alcohol. And then through 4 steps, I can get this molecule called muscone, which is a ketone, cyclic ketone. And they have to make this industrially for those of you who like musk-scented colognes and perfumes. And they make it from a sodium borohydride reduction. Okay? So these are useful reactions in that regard. Okay? All right. So I had meant to move. Get back to it. Where was it? Okay, here. So imagine you had this molecule where you have a ketone and an ester. Okay, both of them have carbonyls, but they're 2 different functional groups. And let's suppose you want to reduce the ester all the way to the alcohol. This is what you desire to do. Okay? The problem is that there's no good way to do that. Okay? And if you actually did the reaction where you treated this with, say, lithium aluminum hydride or sodium borohydride, what you would find is that the ketone would actually get reduced and the ester gets left alone. Ketones are more reactive than esters. And so this becomes a problem. You want to do this, but this is what you're going to get. Well, what we can do is we can protect the ketone as an acetal. Okay? And so, if I had moved it correctly, okay, that's what this is all about. So what we can do is we can take the ketone, we can react it with the ethylene glycol, with tosic acid. We can make that cyclic acetal. That just protected the ketone. It no longer has that weak pi bond. Now this is the only thing that has the weak pi bond. Now I can do the chemistry that I want to do here, and I can get my alcohol. And then I can just simply dump this into water with a lot of water and a little bit of acid, and I can remove the acetal and reform my ketone. And so that's where this protecting group chemistry comes in handy. Okay? It's a lot of steps, but it's the way to get what you want from something that normally can't happen. Okay?
So protection, got my question. But so the protection is those 2 brackets right there.
brackets.
We have to have octagon.
This?
Yes, that.
Well, that's an acetal.
So when protection comes, you have to add an aceton.
Acetal, yes.
And then when it goes to reduction, you have to take away the C, the two, the O there, and the.
Mhm.
And so when you deprotect it, you take away the acetone.
Take away the acetal.
Acetal.
Don't say acetone, acetal.
Acetal.
Acetal. Yep.
Acetal.
So you take away the acetal and you get back your ketone. Yep, that's how that works. We also know that aldehydes can be oxidized. This is what happens when you ingest methanol. So methanol gets oxidized by your liver using alcohol dehydrogenase or cytochrome P450. You end up getting formaldehyde. Formaldehyde will cause you to go blind by itself. But then the aldehyde can actually undergo further oxidation to give you formic acid, okay, which is also toxic. So aldehydes like to be oxidized as well. Okay, so that can happen quite readily using enzymes, for example. But there are other examples that are talked about in your book. Okay. This is called the Tollens test, and we'll do this on Wednesday. I didn't have time to get the demo together. But if you take a nice clean flask and you place an aldehyde in it and you add what's called Tollens reagent, which is this silver complex, okay? So it's positively charged silver. Don't worry too much about all the stuff that's going in. It's under basic conditions. The silver will actually oxidize the aldehyde to the carboxylate, which is the anionic form of the carboxylic acid, okay? So what's happening is an oxidation. Well, if something gets oxidized, something else has to get reduced, right? One doesn't happen without the other. And it turns out that the silver, the positively charged silver, picks up an electron and becomes silver metal. And when you do this in a perfectly clean flask and you shake it, the flask actually becomes silver mirrored, and it looks like a mirror, okay? So what I will do is I will make a silver flask in class, and that silver flask will go to anybody who gets a perfect score on exam 3. And so if everybody gets a perfect score on exam 3, I will sit here and make that many flasks, okay? So we will have the silver flask award for exam 3 next Monday, okay? Now the take-home message here, though, we're not going to get to the chapter on carbohydrates. Just isn't going to happen for us, but you're going to learn about this in biochem, okay? What you'll see here, this is just glucose. It's a carbohydrate. This carbon that the arrow is pointing to, notice it has an OH and an O attached to it. It's like an acetal, but it's called a hemiacetal because it's got an OH instead of an OR. These are in equilibrium in solution with what functional group? That's a carbonyl, but which carbonyl? Is it ketone or aldehyde?
Aldehyde.
It's an aldehyde. So glucose actually will ring close to form what they call the hemiacetal form, or it can open up in your bloodstream to form this. These are called reducing sugars. They will reduce Tollens reagent to silver metal, to a silver mirror. And you'll learn in biochemistry that reducing sugars have a role to play in your metabolism and other things. Okay? So, since we're not going to get to the carbohydrate chapter, I just wanted to show this one slide because I think it's kind of neat that you can take sugar and you can make silver mirrors out of it. Okay? This is how high quality mirrors are actually made. Not cheap mirrors with cheap stuff on the back, but I mean real high quality silver mirrors. They make them using this so-called Tollens reaction. Okay? All right. Quiz 11. I need you to turn in 1129. Put your name and your ID number on that. Leave it over there by where Selena is on your way out. And I will see you on Wednesday.
What I need to eat, Grace, just give me all those.